This video will change the way you look at the world. Things that seem self-evident, things no one would think to question, turn out to be far more fragile than they appear. You might find that hard to accept, but consider this. Einstein himself fought against this idea, and history proved him wrong. Every experiment ever conducted has supported it. So brace yourself. Let's begin. There is one thing almost everyone would agree with, without a moment's hesitation. If you want to measure something more precisely, you need better instruments. That is not a theory or a hypothesis. It is the foundation of all experimental science. A better telescope sees farther. A more accurate clock measures better. Every advance in the history of science has confirmed it. For nearly 300 years, no one had any reason to doubt it. Then in October 1927, at the Fifth Solvay Conference in Brussels, something happened. Heisenberg and Max Born jointly presented a landmark paper titled Quantum Mechanics. They closed their presentation with a bold historic declaration. We assert that quantum mechanics is a complete theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. The record also shows that Heisenberg stated, because all experiments are subject to the laws of quantum mechanics, and therefore to the uncertainty relation, the incompleteness of localized knowledge is an essential necessity. The formula itself can be understood as follows. Delta x is the uncertainty in measuring the position of a particle, and delta p is the uncertainty in measuring its momentum. The more precisely you want to know the position, the smaller delta x becomes. And because their product can never be smaller than h bar over 2, as delta x shrinks toward 0, delta p must grow toward infinity. That means you can never measure the momentum with precision. The same logic runs in reverse. You can know a particle's position with precision, or you can know its momentum with precision. Never both at the same time. The sharper one becomes, the more the other dissolves. And this is not a limitation of human instruments. It is a limitation written into the fabric of reality itself. Einstein sat in silence through the formal sessions. As a defender of objective reality and Newtonian causality, the entire notion of fundamental randomness and probability deeply unsettled him. But in the dining rooms between sessions, he kept launching thought experiments aimed at breaking Heisenberg's uncertainty principle. Each morning, he arrived at breakfast with a new mathematical construction designed to prove Heisenberg wrong. It was in this charged atmosphere that Einstein uttered his famous line, recorded for posterity. God does not play dice. Niels Bohr, who was defending Heisenberg, shot back with an equally memorable reply. Einstein, stop telling God what to do. The argument spilled over into every session of the conference. Watching two giants clash so fiercely, the physicist Paul Ehrenfest, a close friend of both Einstein and Bohr, was so moved that he walked to the blackboard, erased all the equations, and wrote a single line from the Bible about the confusion of languages among men. The Lord did confound the language of all the earth. Then he turned and looked directly at Einstein and said something that clearly stung. Albert, I am ashamed of you. You are arguing against quantum mechanics with the very same tactics that the reactionaries used against your theory of relativity. The historical record notes that Einstein heard this, went quiet, and a sad smile. 3 years later in 1930, Einstein returned to the Sixth Solvay Conference with a more sophisticated weapon, the photon box thought experiment, designed to bring down a different form of Heisenberg's uncertainty relation, the one connecting energy and time. Einstein constructed the following scenario. Take a box filled with photons. On the wall of the box, there is a shutter controlled by a precise clock inside the box. The box is suspended from a spring scale to measure its weight. First, weigh the box to determine its exact initial mass. Then, set the clock to open the shutter for an extremely brief interval, releasing exactly one photon, then closing again. This tells you the moment the particle escapes with high precision. Weigh the box again after the photon is gone. The mass difference delta M gives you the exact energy of the escaped photon through Einstein's own equation E equals mc squared. This means both delta T and delta E can be measured simultaneously with arbitrary precision, and therefore the uncertainty relation must be wrong. Historical accounts record that Bohr could not sleep that night. He went from person to person insisting that Einstein's setup could not possibly be right, because if it were, quantum mechanics would collapse. By the following morning, Bohr had found the answer, and the rebuttal he delivered was one that left even Einstein convinced. Bohr pointed out that Einstein had forgotten a crucial element of his own general theory of relativity. When the photon escapes, the box becomes lighter, and the spring pushes it upwards slightly in the gravitational field. According to general relativity, a clock that changes its position in a gravitational field, that is, a clock that changes altitude, runs at a different rate. This is gravitational time dilation. The displacement of the box introduces an uncertainty in the reading of the clock. When Bohr applied Einstein's own equations from general relativity to the spring scale system, a stunning result emerged. The uncertainty in time multiplied by the uncertainty in energy is always greater than or equal to h bar over 2, exactly as the uncertainty principle demands. The photon box, rather than destroying quantum mechanics, had become one of the most elegant demonstrations of its internal consistency, using general relativity to defend itself against the man who built general relativity. To understand why this limit is embedded in the mathematics itself, you need to look at what position and momentum actually are in quantum mechanics. In classical physics, position and momentum are numbers you read off a measuring device. You write them down, and they exist independently of each other. In quantum mechanics, they do not work that way. Position and momentum are operators' mathematical instructions that act on the wave function, and the order in which you apply them changes the result you get. Measure position first, then momentum, and you get one answer. Measure momentum first, then position, and you get a different one. The gap between those two orderings is fixed by a mathematical relation called the canonical commutation relation, or in the more familiar language of physics textbooks, the commutator of the position and momentum operators. That gap is never zero. It does not shrink with better equipment. It does not vanish with more careful technique. It is a constant written directly into the structure of the theory. Also in 1927, a physicist named Earl Hesse Kennard did what Heisenberg had not. He provided a rigorous mathematical proof of exactly how large that limit is. The formula Kennard derived states that sigma x times sigma p is greater than or equal to h bar over 2. This is the precise version used in quantum mechanics textbooks today, not Heisenberg's original formulation. Heisenberg gave us the idea and the principle. Kennard gave us the exact number. If an electron is squeezed into a region extremely close to the center of an atom, its sigma x drops towards 0. The uncertainty principle immediately forces sigma p to spike upward, meaning the electron's momentum can take on values across an enormously wide range, including very large ones. The electron then carries enough energy to escape on its own. Pushing it closer to the nucleus demands more and more energy without any upper limit, so the collapse never happens. That is why atoms hold their shape. Not because the electron is orbiting at a stable fixed radius, as Bohr's early model suggested, but because any attempt by nature to confine it more tightly is immediately met with an explosive surge in momentum. The atom is stable, not because something holds the electron in place, but because nature cannot know exactly where that place is. Now, apply the uncertainty principle to the simplest thing, imaginable, completely empty space. In classical physics, a vacuum is nothing. No particles, no energy, no fluctuations. If you could remove everything from a region of space, including all heat, you would be left with a region of absolute stillness with energy exactly equal to zero. The uncertainty principle says that cannot happen. Heisenberg formulated a second version of the uncertainty relation 1 that applies not to position and momentum, but to energy and time. It states that you cannot know the exact energy of a region of space over an arbitrarily short interval. If you measure the energy of a region during a time interval delta t that is very small, the uncertainty in that energy delta E must be greater than or equal to h bar over 2 delta t. The shorter the time window, the larger the energy uncertainty must be. The consequence is that a vacuum cannot have exactly zero energy. If the energy of a region were precisely zero, you would know it with perfect accuracy, and that violates the uncertainty principle. Instead, even in a perfect vacuum, energy must constantly fluctuate around a minimum value that can never reach zero. Physicists call this the zero-point energy. It is not an artifact of imprecise measurement. It is a fundamental property of space itself. What makes this stranger still is that these energy fluctuations are not abstract. They manifest in the physical world as pairs of virtual particles that continuously pop in and out of existence in the vacuum. A particle and its antiparticle, an electron and a positron, for instance, can spontaneously appear. From empty space exist for an extremely brief moment, then annihilate each other and vanish back into nothing. How long they last is governed precisely by the energy-time uncertainty relation. The more energy a pair carries, the shorter its permitted lifetime, because large energy requires a small delta t, and a small delta t means a large delta E to compensate. This sounds like a purely theoretical idea with no way to test it. But in 1948, the Dutch physicist Hendrik Casimir predicted that these virtual particles could generate a measurable force in the real world. Imagine placing two parallel metal plates extremely close together on the order of a few micrometers in a perfect vacuum. Outside, the plate's virtual particles of every wavelength can appear freely. But inside the gap between the plates, only virtual particles whose wavelengths fit the spacing can exist, much like how only certain notes resonate on a guitar string of fixed length. This means the vacuum energy inside the gap is lower than outside, and that energy difference produces a force that pushes the two plates toward each other. Think of it like a roof being torn off during a storm. The air pressure inside the house is higher than outside, and the pressure difference pushes the roof outward, or more precisely toward the lower pressure side. The same principle applies here. Lower vacuum energy between the plates creates a net force, pushing them together. Casimir calculated the magnitude of that force and predicted it would be measurable if the plates were close enough. In 1996, nearly 50 years after Casimir made his prediction, physicist Stephen Lamoureux measured the force in the laboratory with 5% accuracy. The vacuum is not empty. That measured force is direct evidence. But the Casimir effect is not the strangest consequence of the quantum vacuum. The strangest consequence involves black holes, and it was worked out by Stephen Hawking. To understand what Hawking discovered, you need to return to those virtual particle pairs that constantly appear and vanish in the vacuum. In ordinary space, the story always ends the same way. A particle and its antiparticle appear exist for the brief interval permitted by the energy-time uncertainty relation, find each other, and annihilate back into nothing. Nothing escapes. Nothing is truly created. The whole process unfolds and disappears as though it never happened. But right at the event horizon of a black hole, something different occurs. The event horizon is the boundary beyond which nothing, not even light, can escape. It is not a physical wall. It is an invisible boundary defined entirely by gravity cross it, and the speed required to escape exceeds the speed of light. And since nothing travels faster than light, escape becomes impossible. Hawking realized that when a virtual particle pair appears right at that boundary, the extreme gravitational field of the black hole can intervene before the two particles have time to find each other. One particle falls inward across the event horizon. The other is pushed outward. Once that happens, the outgoing particle can no longer annihilate with its partner, because they are permanently separated by the event horizon. The outgoing particle becomes real, no longer virtual, and propagates out into the universe. To a distant observer, the black hole appears to be emitting radiation. We call this Hawking radiation. But where does that energy come from? If a real particle is escaping and carrying energy with it, what is paying the price? To put it more plainly, how does energy conservation work here? Where does the energy come from? The answer lies in the particle that fell inward. For the total system to conserve energy, the infalling particle must carry negative energy in a way that quantum mechanics permits near the event horizon. That negative energy reduces the black hole's total mass by a small amount. With each pair of virtual particles split apart in this way, the black hole loses a little more mass. For large black holes, this process is extraordinarily slow. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years. To evaporate completely this way, many orders of magnitude, longer than the current age of the universe. But smaller black holes evaporate faster because a smaller event horizon means stronger gravity at the boundary and a higher rate of pair separation. A sufficiently small black hole would evaporate in an instant in a tremendous burst of energy. What makes this discovery more significant than any specific calculation is what it implies for theoretical physics. Black holes had long been regarded as the simplest objects in the universe, fully described by just three numbers: mass, charge, and spin. Hawking radiation showed that black holes are not that simple. They have a temperature, they have entropy, and they are slowly evaporating. This raises a question that modern physics has not yet answered. When a black hole evaporates completely, where does the information about everything that fell into it go? Quantum mechanics says information cannot be destroyed. General relativity says that information is trapped inside. The two theories are in direct contradiction, and that is the black hole information paradox, one of the deepest unsolved problems in all of physics. The uncertainty principle began as a question about measurement. It ends as a fundamental boundary of reality. But its story does not end there, because the uncertainty principle sits at the center of the largest unsolved problem remaining in modern physics. Modern physics rests on two pillars. Einstein's general theory of relativity describes the universe at large scales. Galaxies, black holes, the expansion of space. Quantum mechanics describes the universe at small scales. Particles, forces, interactions at the atomic and subatomic level. Both theories have been tested with extraordinary precision within their respective domains. And within those domains, neither can be wrong. The problem is that they cannot both be right at the same scale. General relativity is a classical deterministic theory. It describes space and time as a smooth, continuous structure, curved by mass and energy in ways that are entirely predictable. There is no probability. There are no random fluctuations. If you know the state of a system, you can calculate its future exactly. Quantum mechanics is the opposite. It is a theory of probability and uncertainty where particles have no definite position until they are measured, where the vacuum seethes with energy fluctuations, and where the uncertainty principle imposes a hard limit on what can be known simultaneously. When physicists attempt to apply quantum mechanics to the gravitational field that is to quantize space and time themselves, the uncertainty principle is one of the things that causes the trouble. At the Planck scale, roughly 10 to the power of negative 35 meters, which is about 20 orders of magnitude smaller than an atomic nucleus, the energy fluctuations that the uncertainty principle demands become so violent that they must warp space and time dramatically. General relativity has no mathematical tools capable of handling that. When you try to force the two theories together, the equations return infinities instead of answers. But that is not the only reason they resist unification. The fact that general relativity is a deterministic theory, while quantum mechanics is fundamentally probabilistic, is itself a deep contradiction. Space and time in general relativity are smooth and continuous. Quantum mechanics suggests that at small enough scales, they must be discrete and fluctuating. These are not surface-level disagreements that a technical fix can resolve. They are conflicting claims about the nature of reality itself. Physicists have spent decades trying to bridge this gap. String theory attempts to describe particles not as points, but as vibrating loops of energy in extra dimensions of space. Loop quantum gravity attempts to quantize the structure of space and time, directly breaking them into discrete fundamental units. Both approaches are advancing, but neither has produced a prediction that current experiments can test. And that is where we stand today. The uncertainty principle stated by Heisenberg in 1927 from a calculation about how to measure an electron led to the wave function, to the reason atoms do not collapse to a vacuum that seethes with virtual particles, to Hawking radiation, and finally, to one of the most fundamental problems theoretical physics has ever faced. A simple principle about the limits of what can be known turns out to run as a thread through the entire structure of modern physics, from the smallest atom to the largest black hole, and all the way to questions about the nature of space and time that we still cannot answer.